Alright, so today we're going to finish up the rest of the material from Chapter 9 by talking about percent yield. So if you will, please go ahead and open up to page 302 of the interactive reader. And just like before with our discussion of limiting reactant and excess reactant, there are a couple of important terms that will be important for us to know when we're talking about percent yield. So if you will, first take about 2 to 3 minutes to read page 302 and highlight the terms that you think are important. Then once you finish, turn and talk with your neighbor about what you learned. So you can pause the video while you do this. Alright, now let's take a look at some of the things you probably picked out. So there are 3 kind of important terms that it's going to be helpful to know. One is the theoretical yield. And that's just the amount of product that should have been formed based on our calculations using stoichiometry. So this is just basically what the math tells us that we should produce in a reaction when we're starting with a set amount of reactant. But however, as we find, when we're actually in the lab, we may not always make the amount of product that we calculated that we should. And so the second important term to highlight is the actual yield. And that's, when we get in the lab, when we're doing the experiment, that's the amount of product that we actually make. And so that brings us to the third term, is that the percent yield, or here percentage yield, is just a ratio of the actual yield, what we actually made, over the theoretical yield, which is what we should have made based on our calculations using stoichiometry. And then, of course, to turn it into a percent, you multiply by 100. And so here's kind of an example at the bottom of the page in which, in this reaction, we should have theoretically produced 5 carbon dioxide molecules, but in actuality, we only produced 4. And you may wonder, well, why? Why might the actual yield be different than the theoretical yield? So let's talk about a couple of these reasons, because they'll come in handy when we're working in the lab to try to explain where error might have entered in. Okay, so here's our question. What can cause a difference between the actual and theoretical yield? So for example, what if you calculated that you should have gotten 10 grams of product, but you only ended up with 8 grams? So if we were to compare those two, if we did an actual yield of 8 over a theoretical yield of 10 and multiplied by 100, that would get us a percent yield of about 80%. So we may say, well, what happened? So here are some possible explanations for things that might contribute to this difference. One of the reasons might be that some of the reactants may have remained unreacted. Maybe the reaction in the lab didn't fully go to completion, meaning everything didn't react, all the way. A second reason might be that as you're transferring maybe the product between containers, maybe like pouring something from a graduated cylinder to a beaker, or transferring something to a weigh boat so you can get the mass, some of the product may be lost, when those liquids or solids are transferred between containers. Some product might be left behind in the graduated cylinder when you're trying to get all of it into the beaker. And thirdly, some reactants, instead of actually forming the products that we predicted in the equation, they may go on to form other kind of different products that we call side products, and this may occur when things like react with oxygen in the air instead of just the reactants that we wanted them to. And so now that we've talked about some potential explanations for the difference between actual and theoretical yield, let's go on to actually use these terms to find percent yield. And so just as a reminder, all percent yield is a ratio of the actual yield over the theoretical yield times 100. So please make sure you've either highlighted or copied down this formula, since we'll be using it in the next few problems. And so as we're working these problems, we're going to need those 2 pieces of information. The actual yield, which is the measured amount of product from reaction, and that will normally be given to you in the problem. And then the theoretical yield, which is what's calculated based on stoichiometry, and that's like all the calculations we've been doing with limiting reactant. So this you're actually going to have to calculate first. Okay, so let's begin by working the problem on page 303 at the top. So it says one industrial method of preparing chlorobenzene, C6H5Cl, is to react benzene, C6H6, with chlorine, as represented by the following equation. And so whenever they provide you an equation, we always want to first make sure to check and see that it's balanced. And in this case it is. There are 6 carbons on each side, 6 hydrogens on each side, and 2 chlorines on each side. So I'm just going to put a little check to remind ourselves that we have checked to make sure it's balanced. And then here's the information they give us. They say when 36.8 grams of benzene react with an excess of chlorine, the actual yield of chlorobenzene is 38.8 grams. What is the percentage yield? So here's the information that we've been given so far. So we're given that we start out with 36.8 grams of C6H6. And they also tell us another helpful piece of information. They tell us that we have an excess of chlorine. So think about that for a second. If chlorine is in excess, then what does that mean the limiting reactant must be? Exactly. So that means that benzene is going to be our limiting reactant. So that's what we're going to base our stoichiometry off of. And then here what they're asking for is they want to know the percent yield. And this is important, percent yield of what? Percent yield of chlorobenzene. So C6H5Cl. Alright. So we know that based on our formula for percent yield, we have to know the actual yield and the theoretical yield. And so in our given, I should have written this down too, but they also tell us that the actual yield is 38.8 grams. Okay? Okay, so now here's the formula written out, so it's a little easier to see. So we've got the actual yield now, and so what we need to calculate is the theoretical yield. How much product we should make just based on stoichiometrical calculations. So let's start off with our limiting reactant. We know that we've got 36.8 grams of C6H6. And what we're interested in is how much chlorobenzene we produce. Now we know if we've got to compare C6H6 to chlorobenzene, those are two different compounds, so we're eventually going to have to go through the mole ratio. So if I'm starting with grams, that means I need to convert to moles using the molar mass. So here the molar mass of benzene is 78.12 grams per every 1 mole. And again, as we're labeling things, they should each have the 3 components. Okay, so if we were to stop here, we would be left with moles of C6H6. But that sets us up now to be able to use the mole ratio that we found in our balanced equation. So what we found is that since both benzene and chlorobenzene have a coefficient of 1, then the mole ratio between them is 1 to 1. So for every 1 mole of C6H6, we should produce 1 mole of chlorobenzene. Okay, so if we were to stop here, we'd now be in moles of chlorobenzene, or C6H5Cl. So now what we're going to have to do is to continue on and convert moles of chlorobenzene into grams. And the reason that is because our actual yield here, 38.8 grams, is in grams. And so when you're using the percent yield formula, the actual and theoretical yield have to be in the same unit. So since we were given the actual yield in grams, we also need to make the theoretical yield in grams too. So again, to go from moles to grams, we're just going to use the molar mass of chlorobenzene. And so the molar mass is 112.56 grams of chlorobenzene per mole. And so when we run that through your calculator, which everyone please do just so you can make sure you're good on the calculations, what we should get is 53.0 grams of C6H5Cl. Okay? And again, it should have 3 significant figures because our given value also had 3. And so what we've just calculated is the amount of product that we should theoretically get based on the amount of reactant that we started with. So this is known as the theoretical yield. Okay, so now we can just go back and simply plug into our formula for percent yield. So the actual yield was 38.8 grams, and we just calculated that the theoretical yield should have been 53.0 grams. And of course, we'll multiply by 100 to get a percent. And so when we do that, we find that the percent yield is 73.2%. And again, in this case, we're talking about chlorobenzene. Okay, so, we almost produced 3/4 of our product, but it's still not the greatest. And so what we also find is that the percent yield is a measure of how efficient a reaction is. So the higher the percent yield is, the more efficient the reaction. And so I'll write that out. Alright, so here it is at the bottom. So the higher the percent yield, the more efficient your reaction should be. Okay, so then now turn the page and by yourself or with your partner, try to work the practice on page 304, talking about the production of methanol. Then when you're finished, you can check your answer with your partner. And so feel free to pause the video so you can do that. But that's all, and I hope that was helpful in talking about percent yield.